This is Professor Pelton. This is Trigonometry, Chapter 1, Section 4. This is Part 2 of the video on right triangle trigonometry. So we're going to use the special right triangles from geometry now. So the special right triangles, there are two of them that we learn in geometry. We're going to use them here. There are more, but these are the ones specifically we're going to use. So in a 30, 60, 90 triangle, which is the first one, the second one is the 45, 45, 90, you have a small leg and you have a large leg. The large leg is root 3 longer, and the hypotenuse is twice as long as the small leg. So the question is, how do we arrive at that? Well, if we take two 30, 60, 90 triangles together, you're going to get a 60, 60, 60, which is a equilateral, equiangular triangle. Thus, if this is t, which makes a whole side 2t. So that's how we arrive at the 2t. Okay, because it's twice as long. Okay? Add the two t's together. So the question is, how do we get the height, which is the altitude that's drawn? Okay, well, we can use the Pythagorean theorem since it's a right triangle. So we have t squared plus h squared equals 2t squared. If we do the Pythagorean theorem with three sides. So t squared plus h squared equals 4t squared. And we'll subtract a t. Subtract 1t, right? That's what we have. So h squared equals 3t squared. Then we'll square root both sides. Square root both sides. So we get h equals the square root of 3 times t, since the t squared square root is t. So that tells us why the hypotenuse is root 3 longer than the shorter leg. Okay, and we can do a very similar proof for the 45-45 triangle, because the rule for the 45-45 from geometry states that the hypotenuse is root 2 longer than the two legs, which of course the legs are the same because it's an isosceles triangle, because it's two 45-degree angles. So we do the same thing. Since it's a right triangle, we can do the Pythagorean theorem. The leg squared plus the leg squared equals the hypotenuse squared. So 2t squared equals h squared. So if we square root both sides, we get the hypotenuse equals root 2 times t, which is the reason why the hypotenuse is root 2 longer than the actual legs, and that, of course, is smaller if we go the other way. So we can use this to solve special right triangles in a faster, more efficient manner. So, for example, if I have a 30, 60, 90 triangle, and I know the shorter side, thus leg, is 5 centimeters, I can figure out the other ones efficiently and quickly. So the longer leg is root 3 longer, and the hypotenuse is twice as long, and they're all referring back to the smaller leg as a reference. Okay? Pause the video, try the student problem for yourself. So the first thing it's asked to do is draw a pseudo-diagram. So we have 60, 30, and it gave us the ladder reaches 4 feet up the wall. Okay, so this would be 4 feet. Determine the length of the ladder, the distance from the wall. Okay, well, that's the shorter leg, which is root 3 smaller, so that's 4 divided by root 3. And the length of the ladder is twice as long as the shorter leg, which in this case will be 8 over root 3 feet. Okay? Alright, so basically you're doing iterations of root 3 longer or smaller, and twice as long for the hypotenuse when you're doing 30, 60, 90s. Okay? Alright, let's try the next page. Okay, so we'll draw a pseudo-diagram for this one. Oh, that didn't work. I'll try one more time here. Come on. I think we're good. Nope, still didn't work. There we go. So there's our pseudo-diagram. So we have 45, 45, 90. Okay, and we're given here that the rope is 10 feet. Okay, So the way I like to remember when I was in high school is if it's a 30, 60, 90, there's a root 3 involved because it has 3 different angles. If it's a 45, 45, 90, there's a root 2 involved because there's 2 of the same angle. So clearly the legs are shorter than the hypotenuse because all legs are shorter than hypotenuses in all triangles, if it's a right triangle. So this is root 2 shorter. And these an isosceles triangle because it's 45, 45. So the other leg must be the same length. You can rationalize the fraction if you need to, but it's not necessary. Pause the video, try the student problems, plural this time. Okay, so we'll try 45, 45. So 45, 45, 90. And we were given the hypotenuse is 120 meters, which means the legs are shorter by a factor of root 3. I'm sorry, root 2. And they are still meters. Okay? Alright, so try the next student problem. And in this case, we have another 45, 45, 45, 45. So we're given a leg, non-hypotenuse one, is 25 inches, which is, since it's isosceles, the other one must be 25 inches. And the hypotenuse is longer by a factor of root 2. Okay? Alright, next page. So we can use this to translate back to the unit circle to get the ones we had from the unit circle video, but specifically for 45, 30, and 60. So if I take a 45-degree angle, it doesn't matter which one you take. So I'll just take this one, and that is my opposite, and that is my adjacent, and of course that is my hypotenuse. So sine is opposite over hypotenuse. So the t's cancel and leave me with 1 over root 2. And you're probably saying to yourself, well, wait a minute, it was root 2 over 2 for the unit circle. Why is it 1 over root 2 here? Well, if we rationalize this, which means multiply by its rationalized root 2 over 2, which is 1, so it doesn't make any difference, that's going to give me root 2 over root 4, which is the root 2 over 2 we had in the unit circle. Whoops, got a little sloppy there. Okay, but I'm going to keep it as 1 over root 2 because I'm going to reciprocate it to get cosecant. And you can drop the 1 on the bottom if you want. So cosine is adjacent over hypotenuse, which ends up being the same answer, correct? Because the adjacent is the same as the opposite in a 45-45, which gives us the same answer, 1 over root 2 and root 2 over 1. Okay? And tangent is opposite over adjacent. So wait a minute, that's just 1 because it cancels. If you make it a fraction, you can reciprocate it. It's still 1 for cotangent. Okay, let's try the same thing for the student problem for 30 and 60. So if I do 30, that is my opposite side, correct? So opposite over hypotenuse is going to give me 1/2. However, if I do the 60, that is my opposite. So that is t root 3 opposite over hypotenuse, which the t's cancel, leave me with root 3 over 2. Okay? So if I do cosine of 30, the adjacent for 30 is t root 3. So, whoops, not 2, t. So we have t root 3 over hypotenuse, which is 2t. So we get the root 3 over 2. And we go to cosine of 60. The adjacent of cosine, or the adjacent of 60 is t. So adjacent over hypotenuse is u 1/2. And you can clearly see, which we knew in the past unit circle, that the 30 and the 60-degree coordinate are switched positions in the unit circle. So for the other values, we can just simply reciprocate 2 over 1, 2 over root 3, 2 over root 3, and 2 over 1. Okay? So if I'm going to do the 30 degrees, that is the opposite over adjacent. So that's t over t root 3, or simply 1 over root 3 when the t's cancel, which would be the sine over cosine, as we can see. So same thing over here. So if we do the the 60 degrees, that is the opposite over adjacent. That is the t root 3 over t, or simply root 3 over 1, which is the sine over cosine. And we can reciprocate for cotangent, root 3 over 1, and 1 over root 3. Okay, so that relates the special right triangles to the unit circle and how those values are arrived at. And as you can see, that the t can change, right? It can skip, because the unit circle is a radius of what? The unit circle is a radius of 1. Okay, or in this case t, which can be anything. So as it scales up, it maintains those ratios of sides to the angle. Okay, so we have some special relationships here, given that it's a right triangle. If it's not a right triangle, then it's not true. But in this case, it is true for the right triangles. Okay, so you take any angle, and you get 90 minus that angle will give you the same value for what its complement is. Okay, so for example, if I did sine here for this angle, the sine of theta is going to be the opposite over hypotenuse, which is a over c. So this angle must be a variant of 90 minus that, because if this angle is 50, this one must be 40. Right? If this one is 30, this one must be 60. They must add up to 90 degrees. So if I do the cosine of 90 minus theta, that's adjacent over hypotenuse. It's the same ratio. Okay? Hence, the complements of each other, which leads to the cofunction identities down here. Okay? And this is the one we just proved. And you can do the same thing for all the other 4 functions. They go back and forth. Okay? So we can use that to swap out trig functions for other trig functions when needed to solve various diagrams and or equations. So we'll do an example down here. So give me the equivalent trig function. So sine of 72 is equivalent to the cosine of 90 degrees minus 72 degrees. So that gives me the cosine, let's see, 8 more gives me the 90, so that's 18 degrees. So that is equal to the cosine of 18 degrees. If you plug this into the calculator, you'll see that there they are the same value. Okay, so let's take a look at that. It's going to be decimals, of course, because it's not nice ones that work out. So we have what? The sine of 72 degrees. Is in degree mode? It is in degree mode. All right, and we had what? The cosine of 18 degrees. Okay, we get the same answer. Okay, and same thing with radians, but again, if you're plugging in radians, make sure it's actually in radian mode. So here, the cosecant, and we need 90 degrees, which is pi over 2 minus pi over 3. So 90 degrees minus pi over 3. So we need a common denominator, so the cosecant, so common denominator 6, so that's 3 pi over 6 minus pi over 6. I'm sorry, 2 pi over 6. I lied, right? Because 2/6 is equivalent to a third. So that gives me the cosecant of pi over 6 is the equivalent to the, oh no, secant. Wow, that was very bad of me. What am I doing? I didn't change the function. I'm sorry. So let's make those changes. Okay, secant is its cofunction. I read cosecant and I kept going with it. So 2 pi over 6. I'm sorry. Okay. So cosecant of pi over 3 is the same as secant of pi over 6. Okay. So cosecant of pi divided by 3. I need to make sure this is in radian mode. And secant of pi divided by 6. We can see it's the equivalent answer. Okay, which of course has to be a ratio of sides, but we don't know what the ratio is there for that. Alright, so tangent is the cotangent, but we don't know what x is. It's just a variable, so it would be something you would see in an equation. So it's just going to be 90 degrees minus x, whatever x happens to be. So that's equivalent to cotangent of 90 degrees minus x. So take your favorite angle, whatever that angle happens to be. Alright, put it in there, it will work. Alright, pause the video, try the student problem for yourself. Okay, so cosine is equivalent to sine of 90 minus 44 degrees. So essentially this is equal to the sine of 46 degrees. Okay, and over here, this is equal to the tangent of pi over 2 minus pi over 12. So equivalent denominators, common denominators, is actually it would be 12, wouldn't it? So if I multiply by 6, that's 6 pi over 12 minus pi over 12 gives me the tangent of 5 pi over 12. Okay, so here, 90 minus x is going to give me cosecant. So secant is simply just x. And you can go back and forth between that to figure that out. Okay? All right, that is the end of part 2.